Have you ever really stopped to wonder what's inside your phone? I don't just mean the apps and the glass screen, but the actual magic that makes it all work. Well, today, we're going to dive into this invisible art form, a technology so important it powers our entire world, yet most of us have never even seen it. So let's kick things off with a little puzzle. Imagine you have to build a huge, complex city. I'm talking streets, buildings, super intricate pathways, and you have to fit it all onto a surface that's no bigger than a tiny speck of dust. I mean, where would you even begin? It sounds like something straight out of science fiction, right? But the answer is actually pretty elegant, and it's the key to this whole thing. You learn to print with light. To get what that really means, let's just take a look at the finished product. These tiny, shimmering silicon wafers, these are the microscopic cities we're talking about, and they are packed with an unbelievable amount of complexity. You know, every single time you use your computer, your smartphone, or even start your car, you are tapping into one of these microscopic worlds. Look, this isn't just some piece of tech. It's the invisible foundation that our entire digital lives are literally built on. So, how in the world is it done? This whole idea of printing with light. It isn't just a cute metaphor, it's the absolute core of how these chips get made. Okay, so the technical term for this whole process is photolithography. Yeah, it's a bit of a mouthful, but the concept itself is actually pretty simple. Think of it like you're using a very, very advanced stencil. The photomask is your stencil. It holds the pattern of the circuit. The light is basically your ink. And that photosensitive material on the wafer, that's the special canvas that reacts to the light. Okay, right. That makes sense. But hold on. How does light create a physical thing? How does it know what parts to keep and what parts to get rid of? Well, the answer is in some seriously clever chemistry. The secret sauce is in that photosensitive material, which is called a photoresist. And it comes in two flavors. With a positive photoresist, wherever the light hits, it weakens the material, so those exposed parts just wash away. But with a negative photoresist, the light actually hardens it, so the unexposed parts are the ones that get removed. And this one choice is absolutely critical. It's what determines if you're carving out the streets of your city or leaving behind the buildings. All right, so now we have our core ingredients: light, a mask, and a resist. So let's walk through the recipe. It's an incredibly precise 8-step process that turns a blank piece of silicon into a mind-blowingly complex circuit. It all starts with being obsessively clean. A single speck of dust can literally ruin millions of transistors. Then, the photoresist gets spun on in a perfectly even layer. After a quick bake to dry it all out, we get to the main event: exposure. An intense UV light flashes through the mask, instantly printing that intricate pattern right onto the resist. After another bake to really set that chemical reaction, a developer solution washes away the parts that were hit by light, revealing the pattern underneath. And this is where the real construction kicks in. Layers can be etched away, or new material can be deposited. Finally, the rest of the resist is stripped off, leaving a permanent part of the circuit behind. And get this is the really amazing part. This entire 8-step process gets repeated, sometimes hundreds of times, to build the chip layer by tiny, tiny layer. All right, so we've just seen the super tiny and microscopic recipe. Now let's zoom all the way back out. What does all this incredible precision actually build for us? What's the real-world impact here? And I am not exaggerating when I say this is the foundation of pretty much all modern technology. It's what we use to make the CPUs and memory that power our computers. It creates the tiny MEMS, those are microscopic sensors and motors in our cars and our phones. It even builds the photonic circuits for fiber optics, and of course, the printed circuit boards that connect everything together. So really, the next time you pick up your smartphone, or you see a medical sensor, or even just get in your car, just remember that you're interacting with a tiny, incredibly intricate world that was built by this amazing process. It really does all start here. But you know how it is, right? Technology never stands still. The real challenge is this constant push to go even smaller, to get into what they call the nanoscale frontier. This relentless drive for faster, more powerful, and more efficient electronics means the goal is always, always the same: go smaller. Just pack more and more transistors into the exact same amount of space. And that puts an incredible amount of pressure on the fundamental physics of photolithography. Now, this process has some huge pluses. Its precision and its repeatability are just perfect for mass production. But it's got its limits, too. There's a hard physical barrier. You see, the smallest feature you can print is tied directly to the wavelength of the light itself. On top of that, the equipment costs a fortune, and the whole process is unbelievably sensitive to defects. So, how do engineers get around that pesky wavelength problem? Well, if the light's wavelength is the problem, you just use light with an even shorter wavelength. And this has led to incredible innovations like deep ultraviolet, or DUV, and now the cutting edge, extreme ultraviolet, or EUV lithography. They are basically using a much sharper pencil to draw these unimaginably finer lines. So, just how fine are we talking here? Well, today's most advanced chips have features that are smaller than 10 nanometers. Now, to put that in perspective for you, a single human hair is about 80,000 nanometers wide. We are quite literally building cities with roads that are thousands of times thinner than a human hair. Which brings us to one last big idea to think about. For the last 50 years, we have used light to print the patterns that built our entire digital age. So what comes next? What new worlds will we be able to create when we move beyond just printing and we can begin to truly sculpt with light, atom by individual atom?